A very important concept in thermodynamics is this concept of a system. And to define a system, what we're really doing is just defining a space that we want to study. And choosing a system wisely can make a problem much easier. Choosing it unwisely makes it more difficult. So keeping track of exactly what you're talking about when you're trying to solve a thermodynamics problem is particularly important. And so knowing where the boundaries of a system are and what is in the system, what is outside of the system, and this distinction between the two is very important. Now, usually systems that we study are fluids, so gases, liquids, etc., or even mixtures of the two. And usually it's just the fluid itself that we study, but sometimes other things are included within the system. The boundaries of the system can be fixed. They can be real boundaries. They can be imaginary boundaries. They can be moving. They can be stationary. So boundaries can be pretty much whatever you want them to be. It's just you have to be consistent once you have defined a boundary and know where that boundary is and exactly what you're trying to quantify within that system. Here's an example where you might have a fixed boundary. We've got a fire extinguisher, and if we imagine everything inside of that fire extinguisher, well then the body of the cylinder could be a fixed boundary. That may or may not be the best system to take, just everything inside of the cylinder, because maybe it would be better to consider only the chemical itself that is being pushed out of the fire extinguisher to extinguish the fire. Maybe it would be better to consider just the gases inside the high pressure gas canister, maybe the volume above the fire extinguishing material would be what we'd want to take as the system. But a simple fixed boundary would be just everything inside of that container. Now obviously as the chemical flows out, if we take the chemical itself as the system, then as it flows out, that upper boundary moves down, right? So that's a moving boundary. But the simplest system might be just one that's a fixed boundary system. Some systems naturally can't be, well, some systems aren't particularly useful unless you consider part of the system to be moving. The pistons that drive your car down the road or push your car down the road are an example of this. So the upper surface of that piston moves up and down, changing the system volume, where the system you would naturally take here would be the gases above the piston. Now often in this class we will draw piston cylinder devices, but we usually draw them upside down from what you would expect in a real engine. So you see the piston above the fluid in the schematic on the right, whereas in the left-hand picture of an actual engine cutaway, the system of interest would be the gases above the piston near the intake and exhaust valves. So the system boundary then would include all of the fluid, the gases inside of the cylinder above the piston. In the schematic off to the right you can see pretty clearly that as the piston moves down, which is that cross-hatched thing, then one boundary of the system is a moving boundary, whereas the others are fixed. Now here is an example of a two-stroke engine or two-cycle engine where there is a power stroke every single rotation of the crankshaft. One thing about two-stroke engines is that they're not particularly efficient. The gas or the gasoline doesn't have much time to burn because of the way it's set up. Instead of having intake and exhaust valves that are a separate mechanical entity, the piston serves as the intake and exhaust valve. And so there naturally is, the difficulty of getting significant time for the gasoline to burn. So scavenging the exhaust gases is a very important thing. If you look at the assembly off to the right, sort of the largest part of this animated diagram, what you'll notice is that the exhaust gases kind of bounce back into the combustion chamber. Well, that's intentional. That's by design. If you increase the flow area, what happens is the flow will slow down, right? It'll decrease velocity. And so then what you've basically got there is a big mass that the next charge can sort of bounce off of and come back into the cylinder to be sort of reburned. And this can increase the efficiency of the two-cycle engine. Now, one thing about this, the design of that, it kind of looks like a muffler, but it wouldn't really muffle the sound, I don't think. The design of this chamber following the piston cylinder device would be very important, and that would be a system we would like to study. So if we imagine boundaries around this, just the flow area section that's increased there, you would have a real boundary that is revolved, and then imaginary boundaries at the inlet and exit, the right and the left of this system. So that system would be something interesting to study, and so you can see an imaginary boundary where really mass can flow across the system boundary. There are many different system types. There are isolated systems where the systems do not exchange any mass or energy with the surroundings or any other system. There are closed systems where energy is exchanged with the surroundings but mass is not. And then there are open systems where both mass and energy are exchanged with some other system or the surroundings around the system. Now, the first example is the thermos there on the left. That is an isolated system, at least ideally, where no mass would cross the system boundary. So you put your coffee in it in the morning, it stays nice and hot, hopefully, throughout the entire morning and doesn't spill. So it's isolated because no mass crosses the system boundary. Coffee doesn't leak out, in other words. And hopefully it doesn't lose energy over the day, right? So hopefully the coffee stays warm. That's an isolated system, or at least something that an isolated system would approximate the behavior of this thermos. In the real world, obviously, the thermos would lose a little bit of energy, but to a reasonable approximation, the energy in the system would remain constant. The system on the right is a solar collection device where solar energy is collected and heats up water in a water heater tank. Here the fluid itself that goes to the solar collector and then to the water heater is part of a closed system. You would not want this water to just pour out into the tank. The reason for that is because the system, needs to survive the winter, right? So the solar collector on the roof of the home would need to use probably water for its heat transfer mechanism or heat transfer fluid, but most likely you'd want some type of antifreeze in it so that in the winter months that water does not freeze and bust the pipes. So it would not work to have this directly exchange thermal energy with the water in the tank. In other words, you couldn't just pour it into the tank. You'd need a separate coil in the tank that this water runs through, and this schematic doesn't show that very well, but that's the way it would be set up in the real world. So if we imagine the water in antifreeze that runs through the collector and then through the heat exchanger in the tank, that water would be a closed system where energy crosses the system boundary, obviously, because solar energy goes into it and hopefully comes back out, right, at the tank to heat your water, but there's no mass that crosses the system boundary. Open systems might be like this underwater jet engine. It's essentially an engine that's a jet that operates underwater. It uses steam to accelerate water, suck water in, then push it out at higher pressure and higher velocity as a jet. But the system here, the interesting part, would probably be the flow from the water inlet to the water exit where steam is added. So you got two entrance streams of mass, both steam and looks like there's some air that's inserted as well as water that comes in the front of this engine, and then high pressure water, I'm sure with air mixed in, comes out the back of this engine. Now the system I'm talking about would be that revolved area or revolved volume from the inlet where water comes in to where the high pressure water jet leaves out the back. And that system obviously allows both energy and mass to cross the system boundary. Any system that's open by default allows energy to cross the system boundary because the mass carries energy with it. So there are three examples of an isolated, closed, and open system. So to recap, the thermos is an example where neither mass nor energy can cross the system boundary, therefore it is isolated. If we take another example for a closed system besides the solar collection system, here's a classic car where, in the summertime, if the windows are rolled up, ideally no mass would cross the system boundary, but energy could, because obviously if you've ever sat in a car during the summertime with the windows rolled up, you know that the sun certainly transfers energy into the car. An open system might be a carburetor's venturi, where air flows through it, and because of the shape of the venturi, The pressure is reduced so that gasoline or whatever fuel is needed can be sucked into the carburetor and then introduced into the engine as an air-fuel mixture. So both mass and energy can cross the system boundary if we're considering the Venturi as the system, and so this is an open type of system. There are many properties of systems that we are interested in. Probably the most important property is temperature, but pressure is a close second. The volume of the system, the mass in the system, the density, the energy, etc., all these things are properties that we are particularly interested in solving thermodynamics types of problems. Now, you're probably interested in one particular property. If you have a propane tank that is used for heating your home, probably the mass in that tank is particularly interesting to you, because as you run low, you won't have fuel for heating your home, and in wintertime that's a bad thing, right? So mass is something you're interested in, but probably the pressure and temperature are interesting as well. Propane tanks actually are required to have a paint on the outside of them that is reflective of infrared energy, and the reason for that is you don't want the pressure and you don't want the temperature to increase in the tank such that the pressure increases also and the tank fails. That can be a problem. As a matter of fact, certain sizes of propane tanks are required to be away from your home by code in case they do experience overpressure. Of course, there are also pressure relief devices and so forth, but that can cause its own problems. If the pressure relief device works and you're leaking propane out, well, now you've got a flammable mixture that could still cause an explosion and is problematic. But anyway, all of these properties of the system are particularly interesting and useful in order to solve thermodynamics problems. If we make a schematic of that propane tank and just abbreviate all of these properties, we might use P for pressure, T for temperature, V for volume, M for mass, rho, the letter that looks sort of like a P, the Greek letter rho, would be the density, and then U is internal energy. So these are different properties. There are others as well that we would be interested in order to quantify a system's behavior and predict its behavior along the way. One interesting thing about properties is to consider what happens when you break a system into two parts. So let's put an imaginary boundary in the propane tank right down the middle so that half of the mass is on one side and half is on the other, half the volume's on one side, half's on the other. One thing you'll note about the pressure and temperature is that they don't really change, right? We've got system 1 and system 2 now, but the pressure and temperature are the same as they were before. That doesn't change, whereas apparently the volume is sensitive to how big the system happens to be. Notice that the density does not change, however, and notice, assuming of course that the mass is evenly distributed about the tank, and the internal energy doesn't change. We'll talk about that more a little bit later, but notice some properties seem to vary with how big the system is and some don't. Those properties that don't vary with the size of the system are called specific properties. In other words, they are per unit mass properties, or they are properties that are insensitive to the extent of the system or how big the system is. So let's consider something like volume. Okay, if we have gas tank A with a mass of 10 kilograms, a pressure of 100 kilopascals, a temperature of 15 degrees Celsius, and a volume of 2 cubic meters, well, if we break that tank in half in our minds, just put in an imaginary boundary in the middle of that tank, well, then the pressure and temperature is still the same, but now half the mass is on one side, half the volume is on one side, and the other half is on the other. But let's think for a minute how we could rectify this. How could we have sort of a volume property that was not dependent on the extent of the system? That seems like an oxymoron, right? I mean, the bigger the volume of the tank, the more volume there is. So how could you have some sort of invariant volume? Well, what you might do is take the ratio of the volume to mass. So we'll use lowercase letters for these types of properties, where we're taking a total property that is, dependent on the extent of the system, divided by the total mass of the system, and we'll call those specific properties. So let's look at the left-hand tank, for example, and take the total volume, 2 cubic meters, divided by the total mass, 10 kilograms. We end up with 0.2 cubic meters per kilogram. Now, in the right-hand tank, tank B, that has been broken into two parts, at least in our imagination, we could do the same sort of thing and calculate a so-called specific volume. Let's just take the left-hand side, for example. It has a volume of 1 cubic meter with 5 kilograms of mass. That ratio, 1 over 5, is still 0.2 cubic meters per kilogram. So this property that we've defined as volume per mass is what we would call specific problem, and it does not depend on the extent of the system, assuming that the mass is, evenly or uniformly distributed about the tank. Now, one thing to note about this property we've just found is not really anything new. The specific volume thing is actually the inverse of density. Density is just mass per volume. What we've calculated here is volume per mass. So specific properties are just per unit mass properties, and they allow us to have properties that are invariant with the size of the system. A lot of times it's inconvenient to consider an entire system, and more convenient to consider just the properties of the system on a per unit mass basis. So how would you figure out specific properties? Well, you'd measure them, right? You'd take the total property and divide it by the amount of mass in the system. So if we have a 1 cubic meter block of something and we measure its mass, find that it's 3 kilograms, we could take the cubic meter, divide it by 3 kilograms, and come up with the specific volume of 0.33 cubic meters per kilogram, which is obviously just the inverse of its density. Now, there is a property, or there is a thing that is called specific gravity, and it is not a specific property. It's sort of the joker in the pack. In my opinion, it's misnamed. I prefer this be called relative density, because all it really is the ratio of the density of the substance to the density of water at a reference condition. That reference condition is 4 degrees Celsius, where water has a density of 1,000 kilograms per cubic meter. So it's really the specific gravity, or the relative density, is just a dimensionless number that allows you to compare the density of the substance to the density of water. Basically, if the specific gravity is greater than 1, the thing sinks. That's all it really means. If it's less than 1, then it'll float. So oils, for example, have a specific gravity typically, well, all that I know of, have a specific gravity less than the density, or less than 1, meaning that they have a density less than the density of water at its reference condition. Now, the way this specific gravity is typically used is not the way it's defined. What you typically do is you calculate the density of the substance in question from its specific gravity. So you multiply the specific gravity of the substance by the density of water. So unfortunately, this is given the name specific gravity. As I said, I prefer relative density so we don't get confused about specific properties. Now, some systems are uniform. What that really means is that there's no change in any property of the system as you move around within the system. So notice that this was something that was really important in defining a specific property, right? Because for the system, remember the tank that we cut in half in our minds, and half of the mass was on one side, half was on the other. Why? Well, because that was a uniform system. The mass was uniformly distributed within the system, allowing us to imagine specific properties that were invariant with movement around the system because the system was uniform. So a lot of systems need to be uniform for our calculations to work. Now, some systems in the real world are reasonably uniform, some simply are not uniform. So you can get into some other interesting behaviors when you have non-uniform systems, but most of the systems we talk about in this class will be uniform systems. If you're confused about what a uniform system is, well, imagine a pancake griddle where you're trying to cook pancakes, and you want the pancakes to be nice and, uniform golden color across the entire surface. Well, if the griddle you're cooking on does not have a uniform temperature, in other words, is invariant in temperature no matter where you move across the griddle, then some pancakes are going to burn and some will not even cook, right? I cooked some pancakes for some friends of mine where their griddle wasn't quite as uniform as the griddle I typically use, and there were stripes across the pancake where obviously the temperature had been higher and the pancake just was farther along the reaction than at the outside edges of the pancake. So it was less uniform than ideal, and ended up making pancakes that still tasted pretty good, but they weren't quite as good as they could be if the surface was nice and uniform. Now, systems go through various states. Saying that a system is uniform does not mean that it is unchanging, right? As a system can change with respect to time, and one collection of properties at particular levels represents a state of the system. And I like to think of states as my bank account. Okay, so a bank account, whenever you get your statement every month, you know, whether it's online or by paper or however you do that, maybe you look it up on your smartphone, you can look at one particular property that you're probably really interested in, and that's your account balance, right? And that state might change from time to time and go to different levels of that property, right? In other words, you could have more or less money in your account. Now, in thermodynamic systems, the properties, you know, at one value is a state of that system. So if you look at something like a piston cylinder device, you see I've laid one on its side here to illustrate the volume of the system. Well, as that piston moves, the amount of volume within the system changes. The system state changes, and you can imagine that the pressure, temperature, the amount of energy, and so forth in the system would change as well. But the collection of those properties at one level is the state of the system. Now, we will often assume that we have so-called equilibrium states, and what that means is that as a system moves from one state to another, everything within the system is at equilibrium. It's all balanced. In other words, if we just move from state one to some other state and just let it sit there, that state would never change, right? It immediately reaches equilibrium when we move to that new state. So this requires balance in thermal, for example. So the temperature has to be the same or uniform throughout the system. That's an equilibrium state. Otherwise, if there was a difference in temperature from one end of the cylinder to the other, well, then heat's going to flow in the direction of the thermal gradient, right? So that would not be equilibrium. And so one of the things that we require for equilibrium states is that the system be uniform. Mechanical or force and pressure equilibrium is required as well. So if you imagine pushing the piston really, really fast, well, then the pressure is going to build up higher near the surface of the piston quicker than at the other end of the cylinder. It takes some time for the pressure wave to get to the other end of the cylinder. Not very long on a human scale with most typical gases, but it still takes some finite amount of time. We're not assuming that that happens when we have equilibrium states. Phase equilibrium is required, chemical equilibrium, all these things are required in order to have equilibrium states, which is how we assume systems proceed from one state to another along a process path. Now, if you think about a real piston cylinder device, maybe the one in your car, where the gasoline and air mixture is in the top, the piston has compressed it, and the spark plug lights it up, is that a reasonable estimation, or does the system follow equilibrium, right? Is it at equilibrium? Well, obviously not, right? I mean, when the spark lights up the air-fuel mixture, the properties of the local system around the spark plug are very different than the properties ahead of the pressure wave near the surface of the piston. And that difference means that there are things that are going to happen, right? There are chemical reactions that are going to happen as the flame front expands and the fuel and air mixture burn. There's a difference in pressure wave, the pressure before and after the pressure wave, and of course within the pressure wave as well. So there's all these unequilibrium things, and so really equilibrium states are not something that are very exact in the real world. In other words, they're not something that happen very often, okay? Does that mean that it's a totally worthless model? No. It's still a useful model where we can learn some things about real systems. It's just understand we're making some approximations here so that our math and our analysis is simplified. So we will assume that as a system moves from one state to another, that it moves through equilibrium states and therefore is a quasi-equilibrium process. Now, this is not such a bad approximation for the kinds of problems that we are going to solve, but we will always assume that processes move through a quasi-equilibrium process from one state to another. Now, these don't really exist, but they are easy to analyze, they would produce the most work, and they're typically good approximations, at least where at our level we can learn something about how these systems really behave. Now, if we had a non-quasi-equilibrium process, then that process could still move from one state to another, but we wouldn't really know much about the process path. We wouldn't know how the system moves from one state to another. that still may be useful because sometimes all we care about is the initial and final states. For example, think about your bank account again. Do you really care? Let's say you checked your account balance one day and the next day you found that it had increased by $1 million. Well, you may or not really care about how that happened, right? And now obviously there could be a mistake, and that would be sad if you had $1 million apparently one day and the next day you didn't, right? So you might actually care about the process path, but you know, obviously you wouldn't want the process path to include things that were unethical. But a lot of times the initial and final state of the system is what's important. Let's take a more mundane example. You know, you don't really care that you either had to get the check from your employer and go deposit, or if there's direct deposit. What you care about is that the state of your bank account went from lower dollars to higher dollars and that you were paid, right? So the initial and final states, often in an equilibrium or in a thermodynamic system, we don't care whether it went from one state to another via a quasi-equilibrium process or not. It's just in non-quasi-equilibrium processes we can't say a whole lot about the process path. Now, there are a lot of processes that move a system from one state to another that are simpler. There are assumptions we can make. There are simplifications that we can use in order to make our job of analyzing the system easier. There are so-called isentropic processes. Now, let's try to guess which one is which. So an isothermal process, you might guess that is, well, what do you think? Think about it for a second. Thermal. What do we usually associate thermal with? Well, temperature. So isothermal simply means a constant temperature process. Isobaric, well, bar is a unit of pressure that's probably not used as much anymore as it used to be, but it is a unit of pressure. So iso means constant, and baric, or isobaric process, would mean a constant pressure process. Isochoric or isometric means constant volume, and then isentropic is constant entropy. So you can see how these match if we played basically a matching game here. Okay? Now these are simpler processes where something is held constant as the system moves from one state to another. Now you might think, well, how could a system move? If you're saying that this property is held constant, could the system change at all? Well, yes, there are other properties of the system that could change. You know, if you think about an isothermal process, the volume could potentially change as the temperature is held constant. That is a possibility, certainly. There are also steady flow processes. Now, in these steady flow processes, often they are non-uniform. In other words, if you look at the properties at one point within the system versus another location in space, you will find that the properties of the system vary between those 2 points. They're not the same. But over time, those properties don't change. So if I look at the inlet to this continuous stirred tank reactor, the feed coming in does not change with respect to time. The chemical composition and so forth do not change. But maybe there's a reaction occurring where the feed goes from, you know, component A to component B. Maybe we're using a cooling jacket so that the reaction doesn't happen too fast or something. But the exiting product, B, is different than the entrance feed, A. And obviously somewhere in the system, if the system is just the stuff that's being stirred, well then that system can't be uniform, right? Because at some point, feed A has to change to product B. But the idea of a steady flow process is that no property at any particular point changes with respect to time. So we've got this concept of what a system is, and that system could have states, and that those states might move from one to another via processes. What if we took a bunch of processes and strung them together so that the system ends up back at the state where it began? Well, then we would call that a cycle. Now, this is an example of an Otto cycle, and we'll learn more about this cycle a little bit later. But this cycle is the typical cycle, the most basic cycle for a spark ignition engine, the type that you probably use in your car to drive around. Now, the processes within the cycle model either the piston cylinder device you see on the right or even the Wankel engine you see on the left. We don't really see a big difference between the two because our model is so crude. There's so many assumptions that have been made, whereas the mechanical details and the efficiency and so forth of these engines are in fact very different. But the basic behavior of these two engines can be modeled by this cycle, and the cycle does predict some very important things about the efficiency of both of these engines that we will see later. The important feature to note right now is that the system moves through 4 distinct states via 4 distinct processes and ends up back where it started. So you move from state 1 through isentropic compression to state 2, then you move from state 2 to state 3 by constant volume heat addition, then from state 3 to state 4 by isentropic expansion, then from state 4 to state 1 by constant volume heat rejection. And as I said, we'll study this later. But this cycle occurs over and over and over as the engine generates power in a repeated fashion, a cyclic fashion. And we can learn quite a lot from these cycles. They can model, within a reasonable approximation, the behavior of these engines. Now we need to talk a little bit more about systems. There are so-called simple compressible systems. In real systems, there are a lot of effects, a lot of things that change the system, some more and some less. But we're going to neglect a lot of the minor effects on systems. For example, if you think about your car going down the road and you turn a corner, for example, that motion will certainly affect the gases inside of the piston cylinder device, inside of your engine. But does it affect those gases to a large extent? Not really. I mean, you can think of the gases in the chamber as sort of sloshing around as you make a curve, but that effect is so small it's not really worth talking about, because the piston is moving up and down in the cylinder so quickly that its effect on the gas is much more pronounced than the bulk vehicular motion. In the same way, gravitation does act on those gases, and so if you have an upright piston cylinder device, for example, the pressure at the bottom of that cylinder is going to be just ever so much slightly higher than at the top due to gravitation. But that is a very small effect. All these different things, surface tension, magnetic fields, electric fields, gravitation, and motion, are things that we will typically just neglect because they're not the main thing. I mean, if you think about, you want to get rich, let's say, okay? So what do you do to get rich, or at least to increase your income? Well, one thing you might do is you might get lucky and find some money along the road, right? That might have an effect on your bank account. Just the other day we were walking along and there was $1 laying on the ground. I have no idea who dropped it. There weren't any people around. And so I pointed it out to my daughter and she picked it up. Now for her, that's a reasonably large change in her bank account, right? Because she doesn't have a job. She's just in school. She's a little girl right now. For me, it wasn't like I really needed that dollar. That would not have been a significant effect on my bank account. I make most of my money by teaching, obviously, right? This is my job. This is what I do. So this would have been a minor effect. So to include that dollar, if I were to pick it up instead of her, what effect would that really have on my bank account? Well, not much, right? Obviously, I gave it to my daughter because I wanted her to have the feeling of happiness, of a larger change relative to her everyday money accumulation, right? She doesn't accumulate money every day. Maybe she gets it for birthdays or whatever, but it's a bigger effect on her than it is on me. So it was a negligible thing. In the same way, a lot of effects on systems are negligible and not worth considering. All right, so now let's approach the state postulate. I'll read it to you. The state of a simple compressible system is completely specified by 2 independent intensive properties. Remember before we talked about different special types of processes that were, say, operated at constant temperature, where one particular property, temperature, did not change with respect to, I don't know if I want to say time, but with respect to the motion from state 1 to state 2 of the system. Well, how many properties can we hold constant? If we have just, say, air inside of a piston cylinder device, how many things can hold constant? In other words, how many of the properties are related to one another? Well, you remember the ideal gas law, PV equals nRT, right? Well, that gas law relates some properties of the gas to one another, pressure, volume, and temperature. So if you think about it, air is a simple compressible system, and so if we compress that air, say we change its volume, then its pressure and temperature can change, right? But changing the volume of the air does not dictate what the pressure and temperature do. They would both change, but how much? You still have a degree of freedom there. You got to specify 2 things in order to specify the third. So you'd have to specify the pressure and the temperature of the air, say, to specify the volume or to calculate the volume. So for simple compressible systems, it only takes 2 independent intensive properties, where the intensive properties, what that means is they are specific properties per unit mass, or properties that do not depend on how big the system is. Now, Gibbs phase rule is something you probably have not heard of before, but when you have more than one phase present, you can calculate the number of independent properties that must be specified to fully declare or define the properties of the mass in the system. So the number of independent properties on the left is equal to the number of components in the system minus the number of phases plus 2. Now, you probably already know this from your everyday experience. You know that water, for example, boils at 212 degrees Fahrenheit or 100 degrees Celsius. How do you know that? Well, let's think about it from Gibbs phase rule. How many components do we have when we're boiling water? One, right? One chemical component, it is water. How many phases are present? Well, when boiling occurs, there are two phases. There is steam, and then there's liquid, right? So there's gas and liquid. So that's two phases. One component minus two phases, right, gives us -1, plus 2 is +1. So there's only one thing we can specify. And you might say, well, that doesn't make sense because, you know, how do we specify anything? The water has to boil at 212 degrees Fahrenheit. Does it? Really? If you were to go to the Himalayas, if you were to increase your elevation, water would actually boil at a lower temperature. So what property is it that you're specifying? It's pressure, right? So at sea level, water boils at 100 degrees Celsius, or at least fresh water boils at 100 degrees Celsius. But as you decrease the pressure, water will boil at a lower temperature. And so you've naturally already specified a property, and that is pressure. That's an intensive property. And then when two phases are present, in other words, when there's gas and liquid, everything else is fixed. The specific volume, the temperature of boiling, and all these things are things that are fixed and unchanging. Now, systems, of course, can possess energy. That's one thing we're particularly interested in. That's the whole point in studying systems in the first place. Kind of like the whole point of having an account down at the bank is to have money in it, right? So there's many different forms of energy that a system can possess. There's thermal energy. This is basically the motion of the molecules on the molecular scale. There's potential energy, so the location of the mass of the system within some type of field. There's kinetic energy, right? There's the motion of the system. There's mechanical energy. Think of springs. And I've used this graphic because it's sort of a light-hearted thing. Hopefully it gets a chuckle from you. But it's a propane tank that has been made to look like a pig, right? So there's spring legs that have been added. That could be some mechanical energy. Maybe if there's gas inside of this, we'll take the whole pig as a system, okay, not just the fluid, but if there's gas inside of it, there could be pressure. That's not really potential energy as much as it is mechanical energy. Technically, though, it would be caused by thermal energy because the gases inside would be bouncing around, generating the pressure in the first place. If we've got this thing on a wire rope and it's swinging around, then it could, you know, be transferring some potential energy to kinetic and vice versa as it swings. We're really stretching here, but it could have some electric energy if it's charged and moving within an electric field. It could have some magnetic energy if it can be attracted by a magnet or something, and we're really stretching here. Chemical energy wouldn't be too much of a stretch. It is a propane tank after all. If there's some propane left in it, well, then I don't know who would have been brave enough or stupid enough to weld to it, but there we go. And there could be some nuclear energy. There could be some atoms that are, decaying over time. Probably a very small percentage, but background radiation is a real thing. So all of these things would add together and represent the total system energy. Now, this is not so foreign to you. If you have a bank account, you might have a checking account and a savings account, or you might have a certificate of a deposit or some type of money market, or maybe you have a safety deposit box that has valuable things stored in it. That's already 5 different types of value that your bank account could hold. In the same way, systems can hold many different forms of energy. Now, the ones that we're really interested in are really the thermal and, mainly thermal energy. That's the biggest one, as well as chemical energy. But sometimes we'll deal with potential and kinetic energies as well as mechanical energy. But the other ones, the nuclear, the magnetic, and the electric, in this class we're not going to deal with hardly at all. But all of these do technically sum to the total system energy. So what is pressure? Is pressure something you feel when you're getting ready for an exam? Well, no, maybe stress would be a better name for that. But pressure is something that is experienced due to, a gas being confined or being acted upon by gravity. If you were to try and measure pressure, say of your car tire, you would probably use gauge pressure. So you would take a gauge and you'd measure your tire pressure, and what you're really measuring is the pressure of that tire above and beyond atmospheric pressure. Okay, so if you consider how pressure works, if you go into outer space, right, up beyond the clouds and the atmosphere and so forth, you'll reach essentially a vacuum. Okay, it's close enough to absolute zero pressure to call it zero absolute pressure. Now, if you take a vacuum gauge to space, then what it would be reading is the pressure below atmospheric. So this is, it would read, say, 14.7 psi of vacuum out in space. On the other hand, if you come down to ground level and use a regular gauge pressure gauge, then it would read zero at ground level, whereas the absolute pressure gauge would measure the pressure of the atmosphere. We really live under an ocean of air, and what does it mean to have 14.7 psia, or pounds per square inch? Well, what that means is that every square inch of surface area on your body, and if I look at my hand, I've probably got, what, 1, 2, 3, 4, at least 4, maybe 5 square inches here just in the back side of my hand. Well, each one of those square inches has 14.7 pounds of pressure sitting, or 14.7 pounds force sitting on it. Why is my hand not just crushed, right? Because that's well over 50 pounds. And what am I doing, weightlifting all day? Well, no. Obviously, the pressure inside of my body is in equilibrium with the pressure outside. What causes that pressure in the first place? Well, it's really just the gas bouncing around, right? If you think about a tank of compressed air, maybe sitting out in your garage, if that tank of compressed air has a pressure gauge on it, and you read, let's say, 60 psia, or psig. If the temperature of that air in the tank goes down, what happens to the pressure? Well, the pressure goes down too. Because what's generating the pressure is the thermal energy. It's the gases bouncing around within that tank that push on the pressure gauge and register a reading, right? And if they're not bouncing around as fast, they're not going to push as hard on the sensor of the pressure gauge, and the pressure is going to drop. What about the vacuum pressure gauge? Well, down at ground level, it would read zero vacuum, right? Because there's no vacuum. It's just exposed to atmospheric pressure. It wouldn't make sense to take the vacuum pressure gauge and go diving, but you might take the gauge pressure gauge and the absolute pressure gauge. And if you measured 30 psi-G, then obviously you would have to add atmospheric pressure on top of that to get the total pressure of, say, 44.7 or so psi-A. So these are the scales we typically use. We use gauge pressure quite often, we use absolute pressure, and we use vacuum pressure. And you've got to know which pressure the particular equation calls for. Now, there are relationships between these, obviously, and I've copied them here from your text, but you can write them down or locate them in your book if you wish. Pascal's paradox is an interesting consideration when we're talking about pressure. Pascal's paradox is the idea that the shape of the container doesn't actually affect pressure. It's the depth of the fluid, at least in a static fluid, that determines pressure. So as you move down in a fluid, the pressure increases, assuming you're within a gravity field. So think about swimming in a swimming pool. As you move down lower and lower, deeper and deeper into the pool, the pressure goes up linearly, because the pressure is just, rho GH is just the pressure, or the pressure changes rho GH. And that's the way we usually talk about it. So it doesn't really matter at what the shape of the container is. If you're at the same level within the container, you will have the same pressure. Now, if the fluid changes, say we've got a little bit of mercury somewhere in the pool, and you could dive down into it, well, then as you go down into that mercury, the pressure is going to increase at a much higher rate. And so the pressure at the same depth within the mercury and the liquid, or the mercury and the water of the pool, would be different because you're in a different fluid, or you're moving through a different fluid. Now, usually the equation P equals rho GH is not an equation I really like, because we're usually talking about changes in state. So, say a submarine moves from one elevation to another, that would be a change in state of that submarine system. And to calculate the pressure change, we really need the density of the medium that the submarine is in, probably salt water. We need the acceleration of gravity g, close enough to, the regular acceleration of gravity, and we would need the height change, delta H. The problem is we usually like to take a coordinate system as positive going upward, going towards outer space, away from the center of the Earth. And so if the submarine moves down, then it is moving in the negative direction of the coordinate. So its change is a negative elevation change. Its delta H is a negative number, but the pressure change is obviously going to be a positive thing, right? The pressure is going to increase. And so I prefer the equation I've got shown here, delta P equals negative rho G delta H, because it keeps everything straight for me. Deltas are usually used to indicate two different states, so state 1 and state 2, and the way we usually organize them is final minus initial. So the final pressure minus the initial pressure, and then the final height minus the initial height for the delta H. And thereby what we're doing is we're relating the initial pressure and the initial height and final height are in the same position in the equation in the delta, and so are the final pressures and final heights. That way the order is always the same. Okay, so I prefer this equation because it just keeps things straight for me. This equation can be applied in a barometer to talk about barometric pressure, where at the top of the barometer, which is just an inverted tube, there's nearly a perfect vacuum. So you may as well call the pressure there exactly zero. Now understand that is a state. There is a height of the mercury associated with that state, and that height is at the meniscus at the top there of that column. And then the other state is at the bottom of that column at the surface of the mercury bath there, or the mercury in that container. That is a different height of the mercury and a different pressure, but those two are a pair, they're a state, they go together, right? So if we write delta P equals negative rho G delta H, we have to be very careful about which point is which. So the first one, okay, the one at the bottom, at the top of the bowl, at the bottom of the column, that's where atmospheric pressure is observed, and that's where the height of the mercury is zero. So notice we got PATM minus zero. That zero is a pressure zero, it's not a height zero. But over on the right-hand side of the equation, in the delta H, that first zero corresponds to the atmospheric pressure. Those two are together. Those are the properties of a state, right? The state at the surface of the mercury in the bowl. Whereas the minus zero pressure and the minus H height are at the top of the mercury column. So we've been very careful here to match the pressure with its corresponding height in both cases, the case at the top of the column and the case at the top of the bowl. And then the equation works, where you can calculate the atmospheric pressure based on the height of the mercury column, the density of the mercury, and the acceleration of gravity. Now you might look at this and say, well, wait a second, how do you know that's the density of the mercury? Haven't we moved through air? Well, no, technically we haven't. You have to consider what fluid is moved through to get from one state to the other. If you move through the air, you end up outside of the tube, right? You have to move through the mercury to end up inside of the tube and at the desired state where we have a zero pressure. So it's important to keep straight exactly what each of these terms in the equation are talking about. But we can use this equation also to deal with a compound manometer, where basically all you really do is you move down through various fluids, and that makes a corresponding increase in pressure, and if you move up through a fluid, the pressure decreases. Now, an interesting thing about compound manometers is that you can jump from one to the other. So for example, if we're down in the mercury in that first bend on the left-hand side, H4, we don't really have to consider how far down the mercury moves beyond the level of the water in that middle bend, right? All we need is the depth of the mercury from the top of the mercury to the same level in that mercury on the other side of the bend. So that 6-inch dimension is all we really care about. We don't really care how far the mercury goes beyond that, because if you think about it, at the bottom of that 6-inch dimension, if you continue down into the mercury through the bend and then back up, there's no change. This is a static fluid, and therefore the pressure on those two sides would be exactly the same. So that principle allows us to write equations that relate the pressure on one end of the compound manometer to the pressure on the other. And so you see we've written the pressure at A on the right-hand side in terms of the pressure at B, plus a lot of moves through various fluids, some decreasing pressure as we go down in the fluid and some increasing pressure as we go up.